Okay, in the last video, we figured out how to do empirical formulas from masses of a compound. Once it had been broken up into the individual components, we could figure it out, convert it to moles, and solve for the subscripts. What we're going to do in this video is we are going to start with the mass percents, like we learned how to do in a couple videos ago, and figure out how to get back to molecular formula. So basically the opposite of 2 videos ago. So these ones are a little tedious. None of the individual steps are super difficult, but it is what it is. I'm honestly just going to work through an example and kind of write the steps as I'm going, okay? So what we know is, or what we want to know is, what is the molecular formula for a compound with a molar mass, or a molecular weight of, or formula weight, I guess, of 163.7 grams per mole. That is 53.5% strontium, 17.2% silicon, and 29.3% oxygen. So we know the percentages, we know the molar weight, the molar mass, how much the whole thing weighs together, and we need to know what is the formula. So the way I'm going to write this is basically step 1 is you basically apply these percentages to the molar mass. Okay, basically assume you have 1 mole. So we said that 1 mole of anything is going to weigh whatever the molar mass is in grams. So we're going to assume we have 163.7 grams. So we're going to apply these percentages. So for strontium, what you're going to do is you're going to take 0.535, that's this decimal, or this percentage as a decimal, times 163.7. Basically, this would be 53.5% of 163.7. And we're going to get a number for that. 0.535 times 163.7. And I got 87.6, 3 sig figs. Okay. Then we're going to do the same thing for silicon, which is 0.172 times 163.7 grams. We're going to do it again. I got 28.2. And for oxygen, we're going to take 0.293, which is the percentage here, times 163.7 grams. And I got 48.0, I guess I would round up. Okay, that's step 1. Step 2, convert from grams to moles, kind of like we did in the first step of the empirical problems. Okay, so for strontium, we're going to look it up on the periodic table. Its value is 87.62 grams per mole. You'll notice that 87.6 divided by 87.6 is essentially 1. We are looking for nice whole numbers here because we're looking for subscripts. So we should have 1 mole of strontium. Now, for silicon, we're taking 28.2 divided by 28.086. Again, it's going to come out to about 1. We're looking for nice whole numbers here. For oxygen, we're dividing by 15.999. That's the value on the periodic table. And this is going to come out to 3. This is our formula. So the answer is strontium with a silicon and 3 oxygens. This compound is called strontium silicate. Silicate is a polyatomic ion that I didn't make you memorize, but it is technically a valid compound. Okay, these steps, it's tedious to do this 3 times, or if you have 4 or 5 atoms in there 3 or 4 or 5 times, but it's the same thing over and over again. Okay, but we end up at the end figuring out the molecular formula of our unknown compound. Okay, all right, let's try another one, just to make sure you've got more than one example in our notes. Okay, we want to know what is the formula of cisplatin. It is actually an anti-cancer drug. I might talk at the end a little bit about how that works. With a molar mass of 298.0 grams per mole. That is 65.46% platinum, 9.40% nitrogen, 1.35% hydrogen, and 23.79% chlorine. Okay, so same thing we just did, just different numbers, so new problem. So the first step is basically take these percentages and apply it to this amount of grams. So for platinum, we're going to do 0.6546 times 298.0. Okay, and the answer comes out to something, hopefully. 6546 times 298.0. I got 4 sig figs, 195.1. Oops, 0.1 grams of platinum. Now we do the same thing for nitrogen. This is 0.0940 times 298. Okay, 0.0940 times 298.0, and I got 28.0. Oh wait, yeah, 3 sig figs, 28.0. Okay, for hydrogen, we have 0.0135 times 298.0 grams. Okay, and I got 4.02 grams of hydrogen. Same thing for chlorine, 0.2379 times 298.0. Okay, and I got 70.89. Okay, so tedious and time consuming, and I apologize, but this is step 1. Step 2 is to convert each of these from grams to moles. So we look them up on the periodic table. Platinum, if you look it up, is 195.078. (195) divided by 195 is 1. Okay. Nitrogen, the value is 14.007. (28) divided by 14 is 2. Okay. Hydrogen is 1.008. So that basically comes out to 4 moles of hydrogen. Chlorine is 35.453. (70.1) divided by 35.5 basically comes out to 2. Okay. So this is our formula. PTN2H4Cl. And if I was asking this problem on a quiz or exam, this is the answer I would expect from you. Okay. Oh, Cl2, I guess. Sorry. A little bit of detail on this one, just a little bit of backstory. If you're only looking for how to do the problem, you can stop the video now. But if you would like a slight bit of backstory on this, it's actually reasonably interesting. Okay, so this compound looks more like this. You won't know this from this bit of information here, but it's essentially two NH2 groups, so a nitrogen with two hydrogens and two chlorines, both, or all four of these are attached to a platinum, which is capable of forming a +4 charge, so everything works out. The way this works is this molecule is designed to cure cancer. Curing cancer is a very grueling and terrible process for most people because, honestly, cancer cells are almost identical to human cells. And most times your immune system can't tell the difference. So most cancer treatments, like chemotherapy and radiation, the way they work is they basically poison your body, and because cancer cells tend to reproduce so much more quickly, the hope is that if you poison the system, the cancer cells will die first, which is why people on chemotherapy and radiation get so sick. It's their body shutting down. The way this particular drug, which has been around for years, works is really crappy drawing of DNA. DNA. Okay, really bad picture, whatever. What happens is some of the bonds on the DNA will bond to the platinum and kick off a chlorine. And what you'll end up with is this will just float around and float off, not a big deal. It's kind of the same idea as eating sodium chloride, eating table salt. Chlorine is not a big deal. The platinum now bonds to the DNA. Your body has ribosomes which are good at cleaving this stuff off and clearing off the DNA for replication. What makes this so effective is the fact that it does it twice. And because DNA is a huge molecule, it usually will do it in two unrelated spots. So it does this twice, and it's essentially the same idea as tying your DNA in a knot. The ribosomes can't undo it, it can't reproduce, the cell dies. Okay? And if it's a cancer cell, it allows the cancer cells to die quickly. Okay. The problem is this molecule is not in any way, shape, or form specific to cancer. It attacks all the cells equally, and the hope is that because cancer reproduces more quickly, that it will kill the cancer cells faster than your cells, and you will outlive the cancer. I had a professor in college who I don't think he ever finished his work. I think he actually ended up being an administrator rather than a researcher. His goal was to change this molecule. The CLs were important, and he kept one of the NH2s, and what he did was essentially he replaced one of the NH2s with something like estrogen, which is a huge molecule. I'm not going to draw it, I'm just going to write the word estrogen. But the idea is your body would see this, see the estrogen part, and be like, oh, this needs to go to breast tissue, or uterine tissue, or cervical tissue. And if you have cervical cancer, or uterine cancer, or breast cancer, the idea is this is more likely to end up where the cancer is than just floating around all over your body. Okay, so it basically helps target it. It's a pretty genius idea, which is one of the reasons I'm taking the time to explain this. I'm not sure it ever actually got finished. I know when I was his student, the guy, like my organic professor taught me, who I had for organic chemistry, told us about this research. It was pretty profound, but for some reason he couldn't get it published. He couldn't get the results he was looking for, and so he ended up like abandoning it and being an administrator. But if this hasn't been published, if you guys ever make it to organic chemistry or organometallic chemistry and want to fight cancer, this is a pretty viable option. There's other variations on this too. You don't just have to use estrogen. You use like testosterone. Testosterone. Spelling, I can't do it. Anyway. So if you had like testicular cancer, basically this would be more likely to end up where the cancer is. You could customize this molecule, which has already been approved by the FDA, to be able to target cancer where the cancer is at. Kind of profound stuff. Thanks.